start the introduction. So, so I'm a faculty member in the IUR department in that other school in the Bay Area. And so this is joint work with my student, Alfonso Lobos. This was a project that started when I was an intern at Yahoo a couple of years ago. And so this is joint also with Zheng Wen at Adobe Research, and also with Casey Lee, who's right there. Okay, so the topic I'm talking about is profit maximization for online advertising demand-side platforms. So to outline the talk, I'll spend some time talking about the motivation for the problem and our perspective on this problem. And the talk is mainly about optimization. So I'll talk about the optimization model that we built for this problem, some of its properties, and it turns out that this is actually kind of a difficult non-convex problem, difficult in a way that a lot of non-convex problems are not difficult in. And so we use this solution approach based on Lagrangian duality. So I'll talk about that, and then I'll talk about some computation. And this is an ongoing project mainly led by my student now, so we'll talk about the ongoing work. Okay, so I'm sure everyone, or at least 90% of people, know what a demand-side platform is. So DSP is responsible for managing the campaigns of many different advertisers. Essentially, a DSP is about connecting advertisers with publishers through ad exchanges. So basically, a DSP interacts with an ad exchange or many different ad exchanges on behalf of its clients, who are advertisers who want to show their ads. So the DSP basically has the problem of managing the campaigns for many different advertisers by interacting with ad exchanges in a real-time bidding environment. And so effective management for the DSP requires forecasting the landscape of ad exchanges, and basically building really good predictive models, things like that. We focus not on the prediction side, but on the optimization side. So we're focusing on how to actually manage these campaigns, and particularly in a way that balances meeting the advertiser's goals and their constraints, while also trying to maximize profitability for the DSP. So that's our goal, and this is challenging for several reasons. And one of them is because this is a really large-scale problem where the DSP receives as many as 1 million different ad requests per second, and the DSP needs to make decisions in real time. So we have to be able to handle that, and for this reason, often sort of greedy heuristics are employed. Okay, so let me describe in words kind of what the optimization problem that we'll look at will end up being. So we're interested, as I said, in maximizing profit for the DSP. We assume in this paper a CPC or a CPA pricing model. There's some extensions to CPM pricing, but that we're working on. But here we assume CPC pricing. And the decision variables are basically two sets of different decision variables. So when a new impression arrives to an ad exchange, the DSP has an opportunity to bid on this impression. And so they have to decide two things, basically. They have to decide which among my list of clients, among the advertisers who are using the DSP, which of these should I bid on behalf of, and also how much should I bid, right? So who do I bid for, and what's the bid price? And the objective for the DSP, as I said, is to maximize profit. But importantly, there's a balance between profits for the DSP and constraints based on budget constraints for the campaigns, but also constraints that say that the campaigns are doing the things that they want to do. So they're targeting the right people, things like that. And also we need to account for some estimates of the supply of the incoming impressions and model these through supply constraints, as we'll see. Okay, so just to kind of summarize at a high level our contribution. So we develop an approach based on optimization that sort of models the stochasticity in the real-time bidding process and jointly optimizes over allocation strategies. So who do I bid on behalf of, and also the bid prices, which we believe is novel. Okay, so and let me just flash this slide to show where I think kind of this work fits in. So this is just a very simplified view of what I call DSP Analytics Pipeline. So, and this is quite a general thing actually. For a lot of different problems, we're trying to really go from data to a decision, right? And there's a lot of talks today on both sides of here where how do we use data to build a statistical model, whether it's for CTR prediction or bid landscape modeling or something. Here, our work is focused on this aspect of going from a model to a decision strategy. So in particular, we're interested in profit optimization. Okay, so I'll just very quickly mention some related literature. Due to time constraints, I won't get into too many details, but basically, a lot of the literature here has focused on revenue optimization or profit optimization in online advertising from the perspective of various different players. So, so there's been some work related for revenue management for the publisher. Particularly, this Chen paper is related to what we do, but there are some differences in the perspective and the assumptions. Also, revenue management for the ad network itself, and also for an individual advertiser. Here we're looking at a collection of advertisers managed by the DSP, and we want to do profit optimization for them. Okay, so let me discuss the details of the model. So the sort of the basics. So we're thinking about how the DSP should make decisions over a fixed time horizon. Here, I is the set of possible impression types. So we fixed some set of impression types that we could think about as different possibilities for different features. And there's also the set of campaigns that the DSP is managing. And there are these targeting constraints, which basically each campaign says that I want to target a specific subset of the impression type. So I want to target males aged 30 to 40, something like that. Okay, so when we think about modeling the impression types, as I said, so the impression types are sort of defined via targeting. So here I gave a different example of females aged 25 to 34. So that, for example, could be one impression type, but it could be a lot more granular than that, and it always is. Here we're thinking of kind of the impression types as arriving to the system, and each arrival corresponds to a real-time auction, where the DSP has the opportunity to bid in the auction on behalf of one of its clients. And so what we assume is that for each impression type, the DSP has access to a bid landscape forecasting model that's basically been trained on historical data. And what this model gives you is a function, rho I of B, that gives you the probability of winning the auction for impression type I as a function of the bid price B. Similarly, we have another function, this beta I max, which we're thinking about as the expected second price, or really the expected payment to the ad exchange if we win the auction. Also is a function of the bid price B. Okay, and so we also have some prediction for the total number of arrivals of each impression type throughout the time horizon. So so we assume that that's a random variable, but really we just work with this mean. So we just assume that we expect I impressions of type I to arrive during the whole time horizon. Okay. So that's the impression types. And then for the campaigns, we know that each campaign has a fixed budget that they specified. And this is MK is what I call this. So each campaign has specified a fixed budget for this period, and the budget pacing can kind of be incorporated here by how the campaign controls this input. So I sub K is now the set of impression types that campaign K targets, and likewise K sub I is the set of campaigns targeted by impression type I. So those are just the sets that define this bipartite graph linking the impression types to the campaigns that I showed before. And so as I said before, we're assuming a CPC pricing model. So what this means is that every time an ad for campaign K is clicked on, the DSP charges campaign K an amount QK greater than 0. and that happens only when an ad is clicked on. And so this is the CPC pricing model, and we also assume that we've trained some model for predicting the CTR as a function of the impression type and the campaign. So we have these values theta ik, which are the predicted CTRs for users of impression type I and ads from campaign K. And then given these two things, the amount that we charge, the amount that the DSP earns in revenue when a click happens for campaign K, and this predicted CTRs, we get these eCPI values, the expected cost per impression, which is also the expected, so that's the expected cost per impression for the campaign, which is the expected revenue for the DSP, right? So this RIK is the amount of revenue that the DSP earns in expectation when it decides, or rather when an ad for campaign K is displayed to an impression of type I. Okay, so let's talk about the decision variables in our optimization model. So we have two sets of decision variables. Basically, we have to decide two things. Which campaign do we bid on behalf of, and how much should we bid? So we have two sets of decision variables. XIK is going to be a decision variable that's the probability of choosing campaign K to bid when an impression of type I arrives to the system. So so basically, for each impression type I, there's a probability distribution over which campaign we should bid on behalf of. And then BIK is the corresponding bid price, the amount that we actually bid in the auction. So what happens, an impression of type I arrives, we flip some coins with this according to this probability distribution defined by these XIK values, and then we decide which campaign 47, in this case either 47 or 62, do we bid on behalf of. Okay, so let's go through actually the whole sequence of events then. So given these values for the, some fixed values for the decision variables, right, the way that everything works is, this is kind of the first step over here. So basically you flip these coins to determine which campaign to bid on behalf of. So now, suppose that I flipped those coins and I decided to bid on behalf of campaign K for an impression of type I. So what happens next is you have to decide what is the bid price, BIK. So now if I enter BIK as the bid price, I win with this probability rho I of BIK. And so if I don't win, I lose, I'm sad. If I win, then either a click happens or a click doesn't happen. So a click happens with probability theta ik. So if it doesn't happen, I'm also sad. If it does happen, then I earn revenue qk. So it's hidden there, but I earn revenue only when I win the auction and a click happens. So this is kind of the structure of the events. Okay. So given this structure, then we can write down an optimization problem now. So this is the kind of deterministic optimization formulation, which is based on assuming that everything takes on its expected value. So we want to maximize the total expected profit during the time horizon, which is essentially the sum over all possible pairs of impression types and campaigns of the expected revenue that I earn for impressions of type I when I bid on behalf of campaign K. And that depends crucially on the how I did this allocation. So this allocation probability is basically the probability of picking each campaign, and also then the expected revenue in a particular auction for impression type I on behalf of campaign K. And so that's the objective, is the total expected profit in the time horizon. And we have constraints that say that each campaign should not go over its budget in expectation. So the left-hand side over there is the expected spending of campaign K during the time horizon, and we want that to be less than the budget. And then we also have some other constraints that say that basically these XIKs need to define a valid probability distribution. Okay, so let's talk about this problem now for a second. So basically, because of the joint optimization over allocation probabilities and bid prices, this is a non-convex problem. So if I just think about the bid prices as being fixed, then I actually have a linear programming problem, which has been studied quite a bit. So determining the allocations on its own is fairly easy. And similarly, actually, determining the bid prices on their own is somewhat easy, right? So if I have no budget, then it's known that that it's optimal to actually bid truthfully, right, in a second price auction. So actually, without the budget, this problem is easy too. The optimal bid prices are just the valuations, and the valuations are just these eCPI values for the DSP, right, the expected revenue. But because of the budget constraints, right, it may be optimal for the DSP to underbid on an impression right now because there may be a more valuable impression that's coming in tomorrow, right? So so the budget constraints are really what's making this problem difficult. So let's talk about the solution approach now at a high level. So so unlike non-convex problems like training a neural network or something, we can't just throw gradient descent at this problem. We have to think a little bit more clever. So what we do is a Lagrangian relaxation approach, right? So so basically it's a three-phase procedure where during the first phase, we construct a dual problem that ends up being convex, and we can solve that one in a scalable way using variants of subgradient descent. And then we use the solution to this dual problem, these optimal dual variables, to reconstruct the solution to the original problem that we care about. And that gives us essentially a suboptimal but a relatively good allocation strategy and a set of allocation variables x and a set of bid prices b based on using linear programming to do the recovery. Okay, so I'm going to skip the details of how the Lagrangian relaxation works, but basically it's pretty standard. And the kind of key insight actually is that, well, one key insight is that these dual variables can kind of be interpreted as a way to shave the bids, basically, to shave the, so it's a factor that you multiply times the eCPI values that accounts for the budget constraint. So basically, you underbid due to the budget, and the Lagrange multipliers are trying to capture that. Okay. So let's talk about the computational results. So so this is largely an academic paper now. So far we just have some synthetic results, though we're working on some semi-real data sets as well. But for this experiment, or this set of experiments, we constructed some examples where basically we tried to sort of model the idea that some impressions are more valuable than others, and likewise some campaigns are more valuable than others. So we have this construction based on this quality scores where we use this to basically determine the example. So essentially each impression type in each campaign has some quality score that is a uniform random variable on 0, 1, and the number of campaigns targeting each impression type then is a binomial depending on that quality score. So the campaigns, the impression types with higher quality scores have more campaigns targeting them, and similarly, they also have more competitive auction environments. So the ρi functions, the probability of winning goes down if the impression type is more popular. And the CTR also depends on these quality scores. It's basically the product of the two things. And we assume that the campaigns just pay $1 per click. Each campaign always pays $1 every time a click happens. Okay, so we compared basically the policy implied by our optimization approach to a greedy baseline. And the greedy baseline is just based on essentially picking the campaign that pick the campaign that has the highest predicted CTR, and then just bid that CTR. It's very simple baseline policy. Okay, so what we observe is that our approach outperforms the baseline in terms of relative profit. So if you look at the profit of our approach divided by the profit of the baseline, averaged over some runs of the simulation, we have a relative profit of 1.257. But interestingly, where this is coming from, it's kind of the insight of where this is coming from. So the relative cost is very dramatic. So actually, the cost of our approach divided by the cost of the baseline is like 0.28. So we're spending much. So basically, we're losing much less money to the auctions, and also we're actually making less money in total too. So the relative revenue is less than 1. So we're making less revenue than the baseline, the greedy approach, and at the same time, you can see this through the budget utilization. So the budget utilization of our policy is like 48% versus 63% for the greedy policy. So we're using much less budget and basically allocating it in a smart way in order to save on cost. But at the same time, that actually hurts revenue. So these graphs actually show this a little bit in a nice way too. So here we did a similar experiment where we varied the budget parameter from 10 to 50, I think. And this graph on the left in the red shows the relative profit versus budget. So it starts at about 1.12 and goes down to about 1. So when the budget gets high enough, basically the greedy policy becomes optimal. So we end up matching the greedy policy in terms of the profit. But what's very interesting is that even as we increase the budget, the relative cost and the relative profit remains significantly less than 1. So our policy actually is very different from the greedy policy as we increase the budget. But somehow they're actually both optimal. Okay, so to conclude, basically we developed an approach for profit maximization for a DSP that's based on optimization and a two-phase kind of solution approach based on Lagrangian relaxation. And we're currently thinking about extensions. Basically, the whole thing actually relates to model predictive control. And we're thinking about some extensions to other pricing models, things like that, and working with a semi-real data set. So that's it. So thank you.